We're going to talk about the Pythagorean theorem, the distance formula, and the equation of a circle. Now those may seem like three completely unrelated topics, but we're going to find out that they're very closely related to each other. Pythagorean theorem is first introduced in 8th grade, when students are asked to explain the Pythagorean theorem and to be able to apply it to real-world problems and to points in a coordinate system. Now you're probably familiar with the Pythagorean theorem. It relates the lengths of the sides of a right triangle, and it says that if we square the length of the hypotenuse of a right triangle, that distance will equal the sum of the squares of the lengths of the legs of that right triangle. So in this case, C is the length of the hypotenuse, and A and B are the lengths of the legs. Now let's look at a proof of the Pythagorean theorem. And what I'd like you to think about is these two squares that are identical in size, so they have identical areas. We're going to take the square on the left and pick a point on one side of the square, anywhere we want to. And we'll call the distance from the left vertex, the vertex to the left of the point, to the point A, and the distance from the point to the vertex to the right of that, B. In other words, we've taken the length of that side of the square and we've separated it into two lengths, one we call A and one we call B. Now we're going to do that same thing all around the square, using those same lengths A and B. And when we do that, we've got 4 points that are located at specific distances along the sides of the square. Now if we connect up those points, we've created another square. But we need to be able to name the lengths of the sides of that square in order to say anything about its area. So we're going to name the lengths of the sides of that inner square C. Now if you look at those right triangles that surround that inner square, you'll notice that the 4 right triangles are identical in area. Now keep in mind that we started out with a square on the left and a square on the right that had exactly the same area. In the middle, we have a smaller square that has an area of, well, let's see, C times C, or C squared. Now we're going to take these triangles that surround that inner square, and we're going to just rearrange them in our second square, which, remember, had an area identical to the left square. So we've just taken away part of the left square and moved it to the right square, which means that the area that we don't see filled in on the right side has to be equal to the area that we see on the left side that's colored in yellow. So these two areas together have to have the same area as the yellow square that we see on the left. Now we know the dimensions of those two squares on the right side, those yellow squares, because we know the dimensions of the triangles that we use to fill up the square on the right side. We know that those triangles had a base of A and a height of B. So if you look at the two pictures that we have, we know that the area of the yellow square on the left is identical to the areas of the two yellow squares put together on the right. So we can see that the area of the square on the left, the yellow square, is C squared, and on the right, the area of the two yellow squares are B squared and A squared, and those together will give us the area of the yellow square on the left. So the C squared on the left, the area of the yellow square, has to equal the A squared plus the B squared, the sum of the areas of the two squares on the right. So we've got this relationship between the lengths of the legs of a right triangle and its hypotenuse. We can use that to find the length of one of those missing sides if we know the lengths of the other two. So suppose we have a right triangle that has legs that measure 3 units and 4 units and a hypotenuse that measures x units, and we want to find the value of x. Well, according to the Pythagorean theorem, the square of the hypotenuse, so x squared, is equal to the sum of the squares of the other two sides, so that's 3 squared plus 4 squared. That means that x squared is 25, or x is 5. So we can find the length of a third side of any right triangle now if we know the lengths of the other two sides. How about if we have a right triangle and we know that the legs measure 4 and 5 units and we want to find the length of the hypotenuse? Well, we can say that the length of that hypotenuse, x squared, is 4 squared plus 5 squared, which means x squared is 41. Now remember, we want to know what x is, so we take the square root of both sides and we find out that x is equal to the square root of 41. So it's possible that the length of the side of a right triangle could be an irrational number, in this case the square root of 41. Now suppose we have an isosceles triangle. We want to find a length of the height of that isosceles triangle. That isosceles triangle altogether is not a right triangle, but within the isosceles triangle we can actually see a right triangle. That right triangle would have a hypotenuse of 8, it would have a height of x, and it would have another length of the third side, which would be half the base, and half of 6 is 3. So we know that 8 squared equals x squared plus 3 squared. That means 64 is x squared plus 9. Now remember, we're solving for x, so we're going to subtract 9 from both sides and then take the square root of both sides. So x, the height of this isosceles triangle, is the square root of 55 units. What if we wanted to know the area of the isosceles triangle? Well, now we have to remember an area formula for a triangle, which is that the area is 1/2 times the base times the height. And the height is that x that we just found. So the area is 1/2 times 6 times the square root of 55, or 3 times the square root of 55 square units. Now let's look at a three-dimensional figure and see if we can use the Pythagorean theorem to find some unknown measure in that figure. We've got a right square pyramid and we want to find the value of x. Now x in this case is a distance from the vertex up at the top of this pyramid down to the base along one of the sides, and that is a perpendicular distance. That's actually something called a slant height, and we will need to be able to use a slant height when we are finding surface area of three-dimensional figures. But in this case we're just finding the length of x. Now we need to be able to see a right triangle in this picture, and there's actually several of them, but we need to be able to see a right triangle that has some useful measurements that we know. The right triangle's right there. It has a hypotenuse that's equal to that line segment that we're trying to find the length of, that x that we're trying to find the length of. It has another side that is congruent to the height of this triangle, and that measures 30 inches. And it has a third side that is kind of along the base of this pyramid, and it actually goes from that center of the base perpendicularly to the side of the triangle on the base. And we need to know the length of that. But that's not really a difficult thing to figure out because we can see that the square that makes up the base has a side that measures 32. So that length of the right triangle along its base at the bottom would have to be half of that, or 16. So if we just kind of look at that right triangle separately from the three-dimensional figure, we can see we have one side that measures 30 inches. We're trying to find the value of x in the hypotenuse, and then this other side would measure 16. That's half of the 32. So now let's use the Pythagorean theorem. X is the hypotenuse, so x squared equals 30 squared plus 16 squared. 30 squared is 900 and 16 squared is 256. That means x is the square root of 1,156. It would be inches in this case because we're measuring in units of inches. Now 1,156 happens to be a perfect square, and if when you're using Pythagorean theorem you can simplify the radical part of your expression, you do want to go ahead and do that. So the square root of 1,156 is 34, so the length of x is 34 inches. Now the converse of the Pythagorean theorem says that if we have a triangle with lengths that we know, and we take those lengths and we substitute them into the Pythagorean theorem and we get a true statement, then we know that those side lengths of the triangle do represent a right triangle. So the converse of the Pythagorean theorem allows us to prove that a triangle is a right triangle. So let's say we have three lengths of sides of a right triangle, or a triangle. We don't know if it's a right triangle. The three lengths are 6, the square root of 13, and 7. And we want to know if they are lengths of the sides of a right triangle. So what we need to figure out is which of these numbers is the largest number, because the largest number, if this is a right triangle, would be our hypotenuse. So think about the three numbers, and obviously 6 is not the largest number because 7 is bigger than that. So the only question is the square root of 13 larger than 7? And it definitely is not, because the square root of 13 has to be somewhere between the square root of 9 and the square root of 16. And I'm thinking of 9 and 16 because they are perfect squares. So 13's between 9 and 16. Let's see, the square root of 9 is 3 and the square root of 16 is 4. So the square root of 13 is somewhere between 3 and 4. Definitely not bigger than 7. Which means 7 is our hypotenuse, and that, remember, is always going to be our value for c in the Pythagorean theorem. So we want to know if 7 squared equals 6 squared plus the square root of 13 squared. And you notice the question mark above the equal sign. That means I don't know if they're equal. If the two sides of the equation are equal, then we've got a right triangle. So let's simplify. 7 squared is 49, 6 squared is 36, and the square root of 13 squared is 13. And we find out that 49 equals 49 is our statement, which is certainly true. So since that is a true statement, we are going to say yes, the lengths definitely could be the sides of a right triangle. If we have 2 points in a coordinate plane and we want to find the distance between the 2 points, we can use the Pythagorean theorem to find that distance. So we're going to try to find the distance between the points -3, 1 and 5, 6. So let's go ahead and take a look at a picture of that to see what's going on here. -3, 1 and 5, 6 look like that when we graph them on the coordinate plane, and we want to know that distance. Pythagorean theorem relates the lengths of the sides of a right triangle, and all we have at this point is a line segment that we need to find the length of. So we need to build a right triangle off of this. So what we'll do is add to our picture 2 more line segments that create a right triangle that has as its hypotenuse this line segment that we would like to find the length of. Now it's probably pretty easy to see from a picture what the lengths of those two new line segments are. This one is 8 units long and this one's 5 units long. And now that we've got a right triangle that we know the lengths of the legs for, we can find the length of the hypotenuse. Let's call the hypotenuse d, or at least call its length d. And we know that d squared equals 8 squared plus 5 squared. That's just the Pythagorean theorem. So d squared is 64 plus 25. D squared is 89. D is the square root of 89. So the distance between the points negative 3, 1 and 5, 6 is the square root of 89 units. Now you may remember that there is a formula that can be used to find the distance between two points. If we call those points x sub 1, y sub 1, and x sub 2, y sub 2, then what we can do is use the Pythagorean theorem to find the distance between the points. But we need to have a way to express the lengths of the legs of the triangle first. So in the x direction, the distance between the endpoints of that line segment is the difference between the x coordinates of the 2 points that we are using to define the endpoints of the line segment D. And the distance in the y direction is the difference of the y coordinates of those 2 points. So the Pythagorean theorem says that if we square the hypotenuse, that will equal the sum of the squares of the lengths of the other 2 sides. And that might look familiar to you. Actually, this might look familiar to you as well, because this version of that formula, when we take the square root of both sides, is the distance formula that you may remember learning to find the distance between 2 points on a coordinate plane. Now, do you necessarily need to use that distance formula to find the distance between 2 points? Absolutely not. You can use a Pythagorean theorem. But let's see how you do use the distance formula. So let's say we want to find the distance between these 2 points, 4, 3, and negative 5, negative 4. So the distance formula says we need to find the difference of the x coordinates of the points and the difference of the y coordinates of the points. If we square those differences, add them together, and take the square root, we'll have the distance between the 2 points. So in this case, the difference in our x coordinates is negative 5 minus 4, and the difference in our y coordinates is negative 4 minus 3. So that means we need to square negative 9 and square negative 7, add those numbers together, and take the square root. So we get a distance of the square root of 130 units. Now let's see how we could use the Pythagorean theorem more directly to find the distance between those points. If we graph them on a coordinate plane and take a look at that line segment, the length of that line segment is the distance between the 2 points. If we construct this right triangle and then just look for the lengths of the legs of the right triangle, we can see that this leg measures 9 units and this leg measures 7 units. Now look carefully at the work that we did using that distance formula and think about the Pythagorean theorem. We would want to square the lengths of those legs. So we would want to square 9 and we would want to square 7, and we would add those numbers together. So 9 squared is 81 and 7 squared is 49. Look at the next to the last line in all that work we did using the distance formula. There's our numbers 81 and 49. So 81 plus 49 is the square, or the sum of the squares of the lengths of those legs, and we would need the square root of that to find the length of the hypotenuse. Now our last topic is equations of circles. So let's say we wanted to find the equation of a circle centered at the origin with a radius of 6 units. Think about how you would draw a circle with a compass that has a radius of 6 units. You'd put the point of your compass at the origin, you'd measure the length of your compass to be 6 units, and then you would draw a circle that had that radius. And what's important is that No matter what point you look at on that circle, every point on the circle is exactly 6 units from the center. So let's just generalize this and say that every point on the circle has an x-coordinate and a y-coordinate. And every point on that circle has a distance from the center of 6 units. So the radius of the circle is 6. Now imagine that we create a right triangle that has that 6 that's our radius as the hypotenuse, and then it has legs that form a right angle. Now, how can we figure out the lengths of those legs? Well, that leg down at the bottom would have a length of x units if the point on the circle is xy. And the height of that triangle would be y units, once again, if the point on the circle is xy. And according to the Pythagorean theorem, if we square the hypotenuse, that will equal the sum of the squares of the other two sides of the right triangle, so x squared plus y squared would equal 36. And since xy was just any old general point on the circle, that is the equation that describes every single point on that circle. So we can say that the equation of a circle that has a radius of r that's centered at the origin is x squared plus y squared equals r squared. So how can we write the equation of a circle that's centered at the origin with a radius of 10? Well, x and y are the coordinates of any point on the circle. The only thing we need to know here is the radius, which is 10, and if we square 10, we get 100. So the equation of the circle is x squared plus y squared equals 100. So let's take the coordinate plane off of this. And let's still think about a circle that is centered maybe not at the origin. Maybe it's centered at a point, x sub 1, y sub 1. But it still has a radius that we're going to call r. Now how can we write the equation of that circle? Well, we can still think about any point on the circle as having an x and a y coordinate. And we can still think about building a right triangle that uses that radius as its hypotenuse. The length of that bottom leg of the right triangle would be the difference of the x coordinates of those 2 points. So that would be x minus x sub 1. And the length of the other leg of the right triangle is the difference in the y coordinates, which is y minus y sub 1. And the Pythagorean theorem says that if we square each of those legs and add them together, that will equal the square of the hypotenuse. So x minus x sub 1 squared plus y minus y sub 1 squared would have to equal r squared. And that is the equation of a circle that's centered at x sub 1, y sub 1 and has a radius of r. So how can we use that to find the equation of a circle centered at 5, negative 2 with a radius of 3? Well, x sub 1 and y sub 1 are the center of the circle. So x minus 5, because 5 is the x coordinate of the center, squared, plus y minus negative 2, because negative 2 is the y coordinate of the center, squared, equals 3 squared, because 3 is our radius. And if we clean that up just a little bit, we get x minus 5, quantity squared, plus y plus 2, quantity squared, equals 9. So we have an equation that describes every point that's on that circle. So let's think about one more thing with circles. We've seen how to write the equation of a circle. Can we figure out if a specific point lies on a circle? So does the point 1 square root of 3 lie on the circle which is centered at the origin and which passes through the point 0, 2? So let's think about what this would look like. We have a circle centered at the origin that goes through the point 0, 2, which means this would have to be our circle. Now what we want to know is, does the point 1 square root of 3 lie on that circle? There's the radius of the circle. Radius goes from the center to any point on the circle. So obviously the radius of this circle is 2, and it's centered at the origin. So we can write the equation of a circle as x squared plus y squared equals r squared. Now all the points on the circle will satisfy that equation. All the points will make that equation true. So in this case, we want to know if an x-coordinate of 1 and a y-coordinate of the square root of 3 will make this equation true. And remember, the radius of this circle is 2. So does 1 squared plus the square root of 3 squared equals 2 squared? The question mark means I don't know. If it's true, then the point 1 square root of 3 is on the circle. If it's false, the point's not on the circle. So let's see, 1 squared is 1, and the square root of 3 squared is 3, and 2 squared is 4. So 1 plus 3 does equal 4, which means that this point is on the circle. Now if we gotten a false statement, if we had 1 plus 3 equals 5, then we would conclude that the point is not on the circle. So that's 3 different things that are all related to the Pythagorean theorem. We'll get a chance to practice some of this in class.